In this video, we're going to be covering another definite integral. In this case, it is Jn of p, which is the integral from 0 to infinity of cos of x over x squared plus p, to the power of n plus 1, where a is a positive real value and n is an integer that is greater than or equal to 0. So another way of thinking of that is just n plus 1 is a natural number. Okay. So as I've mentioned in other videos, generally the way that I go about things, or I have in the past, has been to give the restrictions at the beginning, whereas now I'm taking more of an approach of actually deriving them as I go along. In this case, it was hard to avoid. The first one I can explain very quickly. So as I said, this should be p. The reason why p has to be a positive value in this case is because if p was a negative value, then that would mean over the region of integration, 0 to infinity, there would be values that would make the denominator equal to 0, and therefore this would become an improper integral. So I'm avoiding that by just forcing p to be a positive quantity. In this case here, n being a n plus 1 being a natural number, or n being a positive integer, is part of a technique. So you'll notice I've used the subscript here, just so you know with all of my videos, whenever I use subscript as a parameter, that means that it's referring to an integer value, whereas if it is a real parameter, or a much more freer parameter, so to speak, a non-integer, it will be within the brackets. So here p can be anything as long as it's a positive real value, and in this case here, n is a positive integer, or n plus 1 is a natural number. Now, this actually is, to look at this on the surface, it's a fairly complicated integral, but we can actually take a much simpler form and then use a few simple rules in order to be able to resolve this, or resolve an expression for it. Okay, so if we just consider the integrand component for a second and create a function of p. So in this case, I've just called it h of p, which is equal to cos of x over x squared plus p. So you can see here, this is the situation when n is equal to 0. If I take the derivative with respect to p, now remember, all the x part are just constant. We have -1, so remember it's just -1 over p plus x squared to the power of 2. And then if I take the second derivative, I have -1 by -2 cos of x over x squared plus p cubed. So remember, we are taking the derivative with respect to p. So you can see here that it's very easy to derive a general expression for the nth derivative of p. So the nth derivative of p, in this case, is just equal to -1. We see just by multiplying the number of times we see the negative, so -1 to the n, and then the n factorial comes from the 2, 1. As I said, if we were to derive this again, the third derivative, that 3 would come up to here, and this would become a 4. And then we have cos of x over x squared plus p to the n plus 1. And so you'll see here, this is obviously the expression that we have in the integrand. So this is critical because this is the fundamental way in which I have decided to take to address this integral. So if I just want this on its own, obviously I just need to divide it over onto this side. And so that's what we have here. Cos of x over x squared plus p to the n plus 1. We see I've just divided through by the n factorial. Now the -1, it doesn't matter if it's on the top or the bottom. I've just moved it up to the top because why not? And hn of p. Now I haven't proven that. If you wanted to prove that, I would just recommend just using a really basic proof by induction, mathematical induction, and that should be able to resolve it. I apologize for the background noise. This is the only time I'll be able to record this, and there's a lot going on in the house at the moment. Okay, cool. So now when we look at this integral, we can actually think of this integrand as this expression here, and that's what we're going to do in the next step. So Jn of p, which is equal to the term that we had before, is equal to the integral from 0 to infinity. As I said, we have resolved this down into this function here, -1 to the n over n factorial of the nth derivative of h of p. Obviously, these are just constants, so we can draw them out the front, which is what we've got here. And then just replacing it for what it is just the nth derivative. In this case, it's the partial because we have x and p within the integrand of cos of x over x squared plus p dx. Now, there's a very famous theorem called Leibniz integral rule, which allows us to, under special circumstances, when integrands follow a certain format, to be able to draw this actually out the front. So instead of taking the integral of the derivative, we can actually take the derivative of the integral, which is what we're doing here. Now, in case you're wondering why it went from a partial to a direct derivative, full derivative, sorry, that's because in this case here, when we're talking about the integrand, there's two variables. However, This integral itself, when you evaluate it, it gets rid of the x because you're integrating over values of x. So therefore, the resultant expression here is just going to be a function of p. And so therefore, it becomes a full derivative with respect to p. And so then what we've got here can be just thought of as -1 to the n over n factorial, which is what we had before, and the nth derivative of k of p, where k of p is just equal to this expression here. So the great thing about this is, once we resolve this expression, we've got our expression for the much more complicated. All we need to do, once we have got k of p, is just differentiate it, n times, my apologies, and then multiply it by -1 to the n and divide by n factorial. So this is what I mean about how we don't actually have to take upon this really, really nasty integral. In this case here, we can take it down to essentially a much, well, what is essentially is a much, much simpler form, resolve that, and then once we have that, we just take the derivative in order to resolve for higher order powers on the numerator. So, fantastic. So in this case here, as I said, we have p, as I said, it should be p up here as well. P is a positive real value, and again, remember, that's because I don't want to have any values of x, which make this integral discontinuous, and therefore it would then be an improper integral, and if it was having an improper integral doesn't necessarily mean it's the end of the world. There are ways of going about it. I just wanted to force that outside of this. So, if you wanted to investigate it for p being less than 0, I highly recommend checking that out. I'm just trying to think off the top of my head how I would go about that. But yes, I can actually think of a couple of techniques off the top of my head. So if people would like to see an exploration for when p is less than 0, please comment or shoot me a message, and I'll do that one up. But for this case, we're just dealing with p being a positive value. Now, coming back to something that I said before, I didn't mention why n was an integer. So why can't we just have it as a real value? Well, because I wanted to be able to use this property of the derivatives. Now, with the derivatives, obviously, it's just going to be integer values that keep increasing. If I had started, though, with a non-integer value, so let's say I started with the square root, it wouldn't be in increments of integers. It would be 1/2, 3/2, 5/2, 7/2. So we can actually include other cases. The reason why I've started with this one is this is obviously the easiest case to begin with, and I'm not even sure if it can be resolved simply with even starting with a square root. But hey, once again, that may be something if people would like to see, I'll give that a go. Nevertheless, let's just jump into this one. Now, this one is actually there's a multitude of different ways we can go about it. I'm going to use a method that lines up with a method that I've been using with a number of the other integrals, which is to employ Feynman's trick coupled with Laplace transforms that requires Fubini's theorem and also the dominated convergence theorem in order to be applied. Okay, so what I'm firstly going to do is introduce a new function, and I'm going to call it L of t, semicolon p, and you'll see here it's just k of p, but I've put a t value within here. Now here I've forced t to be a positive value, but because we know that cos is an even function, if we had used a negative value of cos, it wouldn't matter because cos of negative x is just equal to cos of x. So this restriction here doesn't even need to be there. Cos can be, t in this case can be both a positive and a negative value. It's just that it will always end up giving you the same value because it's an even function. So we can see here, as I've gotten written here, that k of p in this situation here is just L of t comma p when t is evaluated at 1. Now, in order for us to be able to use this function, we need to appeal to the dominated convergence theorem. So just so you're aware of that. And, as I've said in other videos, if you're new to this, don't burden yourself too much with this. But what I'm going to start doing over the next coming weeks is go into more of an explanation as to why this integrand over the bounds complies with the dominated convergence theorem, so that after you get a few of these under your belts and you want to try something new, in order for you to, when you get to the end of it, to be confident, you need to make sure, it's one thing to say, oh, we use the dominated convergence theorem, oh, we use Laplace transform, but just because you use them doesn't mean that the result is correct. You need to make sure, obviously, that the axioms or the assumptions or the impositions, however you want to say, that is required with whatever theorem you apply have been satisfied. Otherwise, we cannot be confident in our result. But anyway, don't let that bother you at this point. So what we're now going to do is we're going to take the Laplace transform of this integral with respect to t. So we see here, we're taking the Laplace transform, transforming t to s of L of t comma p, which equals the Laplace transform of this integral. Now you'll see here in the next step, what ends up happening is I'm taking the Laplace transform of the integral here, but it becomes the integral of the Laplace transform. In order for me to be able to do that, I need to appeal to Fubini's theorem. And once again here, Fubini's theorem is actually satisfied. I highly recommend looking it up, but just so you're aware, we needed that. This step here doesn't just hold for every integrand. There are certain axioms that must be satisfied. In this case, they are satisfied, so just so you're aware of that. Okay, so as I'm taking the Laplace transform with respect to t, anything to do with x is just essentially a constant. So you can see here I've just brought out the 1 over x squared plus b, and I'm taking the Laplace transform with respect to t of cos of tx. And remember here, x is essentially just a constant with respect to the Laplace transform.